10 billion tons a year. That is how much carbon dioxide we will need to remove from the atmosphere every year by 2050 to avoid catastrophic changes to our climate. By 2100, we will need to remove 20 billion tons per year. And we have some choice in terms of how we remove this CO2, as we describe in our introductory video on carbon dioxide removal. But the techniques we choose will invariably require a trade-off. We can choose the most cost-efficient options, or we can choose those methods that will come with the strongest guarantee of long-term CO2 storage. In this video, we focus on the most secure of CDR options, mineralization. Mineralization is like the holy grail of CDR technologies because it traps CO2 into the crystal structure of minerals, thereby permanently sequestering it from the atmosphere. Every other proposed reservoir of CO2 storage comes with some risk of impermanence. Forests can burn or be destroyed by pests. Soils that are cultivated to hold more CO2 may lose it again if land users revert to earlier, more destructive practices. Even storage of CO2 in the pore spaces of underground geologic formations could escape through abandoned wells or along fractures in rocks. But with mineralization, CO2 becomes a part of the rock. There is nearly zero risk of it being re-released into the atmosphere. So let's dig a little bit deeper into the technology. How does it work? And how feasible is it to develop this method as a major pillar of carbon dioxide removal? Removing CO2 from the atmosphere through mineralization is not a novel technique. In fact, it is as old as the Earth itself. Mineralization is the primary mechanism by which the planet regulates atmospheric carbon dioxide over timescales of millions of years. Whenever it rains, CO2 in the atmosphere reacts with water in raindrops, forming a compound called carbonic acid. As the rain lands on the Earth's surface, the carbonic acid reacts with exposed rocks, slowly dissolving the minerals by breaking them down into their metal components. Those dissolved components then get carried by runoff and river water and are ultimately released into the ocean. And because seawater has a slightly basic pH, when these dissolved metals enter the ocean, they react with the carbon dioxide in the ocean to form a carbonate mineral, trapping the CO2 into the mineral structure. This process can happen inorganically, but in oceans today, most carbonate precipitation is facilitated by organisms that use the calcium carbonate to create their shells or skeletons. Every clam, coral, and microscopic foraminifera on Earth is doing its part to sequester CO2 into its mineralized hard parts. And when these organisms die and their shells and skeletons settle on the seafloor and get buried, they are taken out of contact with the Earth's atmosphere, and it will take tens or hundreds of millions of years of plate tectonic processes like mountain building for those carbonate minerals to reach the surface again when they could be exposed to rain and dissolve. In fact, the formation and burial of carbonate minerals is so effective that there is more than 10,000 times as much carbon stored as minerals in sedimentary rock as there is carbon in the form of CO2 in the atmosphere. Unfortunately, mineralization within the Earth's natural carbon cycle occurs on very slow timescales that cannot keep pace with the rates of man-made emissions. At most, natural mineralization removes about 0.7 billion tons of carbon dioxide from the atmosphere every year. Humans emit nearly 40 billion tons of carbon dioxide each year. But what if we could find a way to simulate this natural process and speed it up? Paul Knops is a leader in the effort to engineer a climate change solution that mirrors the natural carbonate mineralization process. Coming from a background in physics, renewable energy, and waste systems, he realized that you could build a high-pressure, high-temperature reactor that mimics the natural mineralization process. By reacting CO2 and water with powdered rock in Mr. Knops' reactor, he is able to recreate the natural processes of rock dissolution and carbonate mineral precipitation that happen in natural CO2 cycles. At higher pressures and temperatures, the reaction proceeds more rapidly. And by powdering the rock, he is able to maximize the reactive surface area of the starting material, which also accelerates the reaction. Another advantage of engineering carbonate mineral reactions is that we can choose our starting material. Rocks that are rich in the minerals olivine, pyroxene, and plagioclase, like volcanic basalts found in Hawaii and Iceland, are far more reactive than average continental rocks. This is because these minerals are rich in calcium, magnesium, and iron, the metals that react with CO2 to form carbonate minerals. And luckily, we have an abundance of basaltic rock on our planet. The upper few kilometers of ocean crust, which covers 70% of Earth's surface, is made almost entirely out of basalt. So anywhere that the ocean crust hasn't been appreciably buried by sediment is a potentially viable mineralization site. But even considering only on-land rock reservoirs, the potential capacity for carbonate mineralization is orders of magnitude more than we need. To remain below 1.5 degrees Celsius of warming, we will need to remove a total of about 125 billion tons of CO2 by the end of the century. For comparison, there are about 12,000 billion tons of CO2 mineralization potential using rocks in the United States and Europe alone, enough to store a century's worth of anthropogenic emissions. Globally, the rock reservoir capacity for mineralization is 60 billion tons of CO2, so the material is there. We just have to figure out the most energy efficient and cost-effective way to use it. Generally, proposed mineralization techniques fall into two categories, which we will explore separately. Ex situ mineralization involves extracting rock from the ground to react with CO2, whereas in situ mineralization involves pumping CO2 underground to react with subsurface rocks. Let's take a look at how ex situ mineralization works. This technique can be one of the most expensive carbon dioxide removal strategies, costing as much as $600 per ton CO2. This is because to remove a high volume of CO2 at a fast rate requires lots of fresh rock and lots of energy to power the mineralization reaction. There are a few ways to reduce these costs, but each approach decreases the realistic capacity of this type of sequestration. Let's consider the reactive material first. For every ton of CO2 we capture, we need at least 1.6 tons of fresh magnesium and calcium-rich rock. We could mine this rock from the ground and mechanically crush it, which is the most expensive and energy-intensive option. Or we could use existing rock waste, either from industrial processes or from the tailings of old mining operations. This could bring the price of mineralization down to $50 per ton. But there is only so much waste material available. The most optimistic estimates would provide about 1.3 billion tons of CO2 storage annually, which is only about 10% of what is needed. Another approach is to develop a source of revenue to offset the cost of energy and primary materials. This is what Mr. Knops' company, Green Minerals, does by selling the carbonate and silica byproducts of the mineralization reaction.
If you make paper, in Europe there's about 6 million tons of lime used in paper manufacturing. They add lime to that for a few reasons. First of all, for the color, make it more white, but more importantly to make it cheaper and to have better properties. And then there is the idea just to use, instead of use the traditional lime, use this material.
Finding a market like paper, which values mineralization byproducts at prices over $100 per ton, could make mineralization a financially viable industry. But how big could this industry be? The European paper market for lime can sequester about 2 million tons of CO2 annually if replaced entirely with mineralization byproduct. That market would need to scale up 5,000 times to reach the 10 billion gigatons of annual CO2 storage we need by 2050. Even if mineralization completely replaced the global market for lime, it would sequester less than 2% of the CO2 needing to be removed annually. There's simply not a large enough market to finance CO2 reduction at the required scale. One final approach to reducing the cost of ex situ mineralization is to forego using an energy-intensive reactor. Instead, Finely ground powders of reactive rock could be spread on beaches, croplands, or surface repositories. This approach, called enhanced weathering, increases the surface area of reactive rock in contact with rain, which speeds up the natural CO2 weathering cycle. Enhanced weathering can cost less than $10 per ton of CO2 if mining waste is used, or $50 to $200 per ton if freshly mined rock is used. And this technique could be employed at a large scale. For example, if we were to cover all 166 million hectares of agricultural land in the United States with crushed reactive rock, enhanced weathering of that material could sequester up to 0.74 gigatons of CO2 in a year. And other nations with large agricultural output, like China and India, have the capacity to sequester similar amounts of CO2. However, a lot of uncertainty remains regarding how this technique would work in reality. First, it is not clear how quickly the powdered material would actually break down, and other possibly hazardous metals could leach from the powdered rock into the soil during weathering. So let's consider our other option, the potential for in situ mineralization. The good news about this technique is that the subsurface rocks don't need to be mined and are already under temperature and pressure conditions that are ideal for mineralization. That means that cost can be much lower than ex situ techniques, ranging from about $10 to $30 for on-land storage sites. And the potential storage capacity is orders of magnitude more than we need. That said, testing how well in situ mineralization actually works is still in its nascent stages. Carbfix, a collaborative research and industry project in Iceland, built the world's first carbon capture plant using mineralization in 2014. The plant works in tandem with an existing hydrothermal power plant atop Iceland's basalt-rich crust. It can scrub CO2 from gases released from the geothermal energy plant or the ambient air. The CO2 is mixed with hot water being pumped for electricity production at the power plant, and the mixture is then pumped into the hot basalt subsurface. There, the CO2 water mix travels through pore spaces and fractures in the rock, reacting to form carbonate minerals. At the Carbfix site, over 95% of the injected CO2 mineralized in less than 2 years. The 6-year pilot program, which is now sequestering carbon at a rate of about 10,000 metric tons per year, has optimized the process such that the costs are around $25 per ton of CO2. This low cost is due in part to the ideal location of the Carbfix project, and costs may be higher in regions less rich in water and geothermal energy resources. But Carbfix provided the proof of concept that in situ mineralization can be affordably achieved. In sum, the possibilities of CO2 mineralization are as promising as the approaches are diverse. However, like other methods of carbon capture and storage, mineralization will require significant upfront investment and government support. It must also be noted that the range in price that we examined for mineralization, from $10 to $600 per ton, only represents the storage costs of the CO2. Most of these techniques require that carbon dioxide is first captured from an emission source or from the ambient air, and then transported to the mineralization site. Those capture and transport costs can range from $25 to thousands of dollars per ton, as we detail in our related videos on carbon capture and sequestration. To learn more, you can find our other carbon capture and sequestration videos on our website, climatenow.com. And you can listen to the complete story of how Green Minerals is helping to build the mineralization industry in our full podcast interview with Knops. Thanks, and see you next time.